Hi, and welcome to this video in which I will resume explaining the introduction parts about algorithms. So last time we just introduced the concept of algorithm and we checked an example of an algorithm calculating the maximum element in a sequence of elements in an array. So today we will expand this a little bit more for different algorithms such as searching a list of algorithm which is still considered as part of the easy problems. So last time we did finding a maximum, which is exactly the same concept as finding the minimum element. To compute the sum of the elements, we also need to iterate over all the elements in the list, so which is almost the same kind of processing for arrays or vectors or sequence of elements that we call list usually. Other types of algorithms are considered to be of intermediate difficulty, such as sorting a list. This will be the topic of my next video. So in this video, I will just talk about searching a list, and I will give two different algorithms for this. Um, and sorting a list is one of the very common problems that we have in computer science, and we have plenty of different algorithms that tackle this problem. Um, One of the intermediate level algorithm could be to merge two sorted lists. We will see this later on, and when we learn about recursive algorithms. Um, and algorithms that are out of the scope of this course that you will see in other courses when you learn about data structures. So you will have to search for a certain node in a certain graph, where nodes, for example, in this graph denote certain cities and edges denote roads between them. And you want to find a specific location on this map, for example. Some of the problem would be hard, such as finding the shortest path in a certain graph between two different nodes on a certain graph, such as finding the best route between two different cities. Another example could be to detect the characters from images, which is called the optical character recognition, OCR, and other image processing algorithms and image recognition algorithms. Or, for example, building a final exam schedule for students while resolving all the conflicts that you may have in this schedule. Yet others are very hard and essentially impossible to solve. For example, prime factorization for very large numbers, and that which is typically used in cryptography to prevent hackers from guessing a certain password, or some problems you will find that they are not even um, um, solvable actually by machines, such as the halt problem or any other paradoxical problem. Let's check some example of algorithm problems. As we said, searching for a certain value in for the position of a particular value or element in a list of elements is one common problem. You do this all the time when, for example, you look up for a specific entry in your phone book to call someone or to message someone on WhatsApp, for example. But this, you will see that when the list is sorted, we can efficiently search within this list. So this is why we keep um, the list sorted, for example, in the phone book application. But many other applications require sorting also. So, for example, your Facebook feed is sorted by date to pick up the latest news, and uh, your WhatsApp messages are also sorted by dates so that you can keep up with the most up-to-date messages. So sorting is a very important problem, and you will see a couple of actually exactly two algorithms in the subsequent video. We can also have some optimization problems to check or to calculate the maximum or the minimum value in a over all possible inputs, and this can be the subject of other exercises here or later on in the practice set. So what about searching problems? The general searching problem is to locate an element X in the list of distinct elements A1 up to AN, or to determine that it's not in the list. And typically in this case, we return a value that does not designate a correct location. So if we find that the element exists at position number I, we would return I, but just in case the element does not even exist in the list, so we return an unexpected value. For example, we return 0 in this case if we start with valid indices at 1, or typically in programming languages, well, arrays start at index 0. So the elements, the n elements that would range from index 0 up to index n minus 1. Okay. So in this case, we would actually return if I is if the element is found at position number I, then we return that position, but otherwise we will return -1 to tell the caller of our search function that the element was not found. So why we use search algorithms. So for example, a library might want to check to see if a student is on the list, on a list of those with overdue books before allowing him or her to check out another book. Also, we search for, as I told you, for feeds coming from a certain specific friend, for a certain message, or for a certain phone book entry, and so on and so forth. So the solution to a searching problem in the location is the location of the term in the list that equals to the element that we are searching for. It means that are equal that equals X. So it means that we return I if the solution is equal to xi, if x is equal, sorry, to ai, or we return 0 if x is not in the list. And as I told you, in effective programming languages such as Python, C++, Java, arrays start at index 0 actually. So 0 means a valid index. Okay, our value could be the first element in the list, and hence in this case we would return 0. So we keep -1 to denote a value that we could not find in the array while searching for it. Okay. So we'll study two different searching algorithms: linear search that goes one cell by one cell inside the array, or one item by one item inside the list until the end of the list to check if any of those elements are equal to X. And another one called binary search that we will see in the sequel. It only works when the array or the list is sorted. Okay, so it does not apply all the time. So only works on sorted lists, but actually you will see that it is much more efficient. So it's more efficient than linear search. Okay. Okay. So we'll see this in later on. So let's start with linear search. The linear search algorithm actually locates an item in the list by sequentially examining elements in the list one at a time, starting from the beginning of the array. Okay. So it first compare X with A1. If they are equal, it returns the position 1. If not, then we try to check if it's equal to A2. If X is equal to A2, then we return the position 2. Otherwise, we check the equality with A3 and so on and so forth. Of course, after checking with AN, if it's equal to AN, we return N. Otherwise, well, we return 0 in this case, or say -1, just a very particular value that denotes that we could not find any match for the value that we are looking for X in the array. So the algorithm would go as follows. So we already discussed in the beginning of this chapter the basic building blocks, so you know that we can make tests using the if condition. But as you notice here, we need to iterate over all the elements of the array. So we need a kind of a loop, either a for loop of type for I equal 1 to n, check if the x is equal to ai, something like that, or a for loop, sorry, a while loop with a counter called I and initialized to 1, and then I is incremented each time until I becomes greater than n, exceeds. It means that the counter I exceeds the possible indices. Um, so no matter what type of loops you want to use, for or while loops, but you need a loop at the end, because uh, by checking only once, well, this cannot cover all the cases. And if you have n elements, then you need n different if one after the other. And if n is variable, if n is the size of the array is given by the end user, then you cannot fix the number of lines of code inside your program. So, well, if you think about it, you know that you absolutely need a loop. So how does it look like? So we start with a counter equal to 1, as I told you, and as long as it is less than or equal to n, we check with a number I. Well, if they are equal, this condition will be false, evaluated to false, and then we will jump outside of the while loop. Okay? But if it happens that x is different than ai, then we have to increment I by 1, and then to be able to check with the next ai plus 1 actually. Okay, so I becomes I plus 1. So if I was 1, on the next iteration, I becomes 2, and then the code that is written here will check with A2. So if you're wondering how to write this in terms of programming, effective programming languages, so I think it depends on the language, but most of them, they would allow you to write not equal in this way instead of the different sign, and then to access an element in an array called A, to access the element number I, we use brackets in this way, just to talk about the element number I. And as I told you, as long as I is incremented, changed within the loop at every iteration, then this means that every time we will test with a different AI, with the first time with A1, the second time with A2, and so on and so forth. Okay, I'm just making sure that we are on the same page. But if you did at least one programming course and you learned about arrays, then I think that you know all these technicalities. When we jump out of this loop, there will be two different reasons, possible reasons. So either because this condition was false, evaluated to false, or because that one was evaluated to false. If this one was evaluated to false, it means X was not different than a certain AI. It means it was equal to one of those AIs. And it means that at that position I, we have found X, okay? And in this case, it means that the other condition didn't have the chance to be evaluated to false, okay? And this is why we would go out of the while loop, because of this condition being false, once again, because of finding X somewhere in the array. And in this case, we can confidently say that the location of the value x in the array is equal to I. Okay, just one tiny note, in arrays in general, we can have just an ordered sequence of elements. So we can have those elements 1, 2, 53, and then 2 again, and then 1, 1, and then 4, and then, okay, so it could be the I don't know, the number of files that certain users have, or the number of mutual friends with every single friend that they have on Facebook. So since for two different friends, I may have the same number of mutual friends, which is two in this case, or for multiple friends, I can have only one friend in common. So those numbers may be repeated. And what we are doing here, if I'm checking who among my friends, with whom among my friends, I only have two different mutual friends, then I will find the first one here, okay? So this algorithm won't continue looking for all the instances that are equal to 2, okay? I'm checking for someone with whom I have 4 different friends in common, okay? So the algorithm won't find 4 here, won't find it there, okay? And will keep going until it finds it here, okay? So even if I is not greater than n, we will stop looking for possible values, because this condition x is different than I becomes equal to false, namely because I have found 4 somewhere. And in this case, we return the index of this value. So this value number 1, 2, 3, 4, 5, 6, 7. Okay, so we'll be returning 7 here. Even if we have 4 somewhere else, okay, this won't be caught by this algorithm, okay? So otherwise, if I is not less than or equal to n, it means that we have checked all the AIs, but unfortunately we didn't find the value. Okay, so x has been found to be different than all the AIs for all the i's starting from 1 up to n included. And simply at that moment, we would have increased I by 1 to become equal to n plus 1. And in this case, when we get back here on the while loop, we will find that I, which is equal to n plus 1 at this moment, is not less than or equal to n anymore. So we will break this while loop and we'll go out of it. But in this case, we won't return I. Fortunately, we won't return n plus 1, although it's an incorrect index, but we will return 0, which also denotes an index that is outside of the array, because the valid indices start at 1. Okay? As I told you, in typical programming languages, we would return -1 here. Okay? So please pause the video if this is new to you. Pause the video, go backward, do it on paper, trace it, and check that this algorithm works correctly. Well, we will have also a certain example, runtime example. So if x is equal to 6, I'm looking for 6 in this array. Suppose the indices are as here on paper, start at 1. So A1 would be equal to 10, A2 would be equal to 15, and so on and so forth. Okay. So now if we want to, and this is 10, okay, so n is equal to 10. So if we want to run this algorithm step by step, at the first step, we initialize I to 1. So we're looking, just in case we are comparing with AI, it means currently that we're comparing with A1. So A1 happens to be different than 6, than X, okay? Because actually A1 is equal to 10. And I, which is equal to 1, is less than or equal to n. So both conditions are true, hence their end is true. And this is why we should get inside the loop and increase I by 1. Okay, so is x is equal to 10? No, actually. And then when we increase I by 2, we'll be looking at a number 2, which is 15, and a number 2 is actually different than 6. So this condition is true. And I, which is equal to 2, is strict less than or equal to n, which is 10. Okay, so both conditions are true. Now we increase I by 1, I becomes equal to 3. And now we should compare with minus 8. Okay, it's still different than 6. I think you got the idea. We increase I, we check if x is equal to a number 4, which is 6. So they are equal. In this case, this condition is false. Okay, because x, which is equal to 6, is not different than a number 4, which is so this is a number 4, which is equal to 6. Okay, um, perfect. And then in this case, we will get outside of the loop and we'll perform this if statement. I is still equal to 4, which is less than or equal to 10. And this is why we will return is I less than or equal to 10? Yes. And this is why we will return 4 as the location where we found x. Okay. And this is why at the end, when we return the location, we return 4 at the end. Okay. So now let's jump to another um, uh, search algorithm that's called the binary search, or the that follows the concept of successive halving. It means looking in halves of the array at each time. We will see what does it mean. So suppose the list, the input list, is sorted in increasing order or in decreasing order. There's always a way. So no matter what is the order, okay, it could be increasing or decreasing, and you see that with a slight change, we can adapt the algorithm. But the most important key here is that the list must be sorted. Well, we can do much better. We can you will see that even if you have 1024 different values, okay, in the array, you can search for them in only 10 different steps. You can find your possible value. You can play this game with your little brother or sister or anyone and just ask them to write down on a piece of paper a certain number between 1 and 1024 and uh, ask them to tell you whether the number that they picked is bigger, equal, or less than the guess that you made. And start by making the same sequence of guesses. Start with 512. If they tell you that the number is bigger than 512, then ask them if it is bigger or less than 512 plus 256, which is 768. Okay, so ask them if their number is bigger or less than 768. If they tell you that the number is less than 500 at the first step, then it could be either greater than or equal to half of that number, which is 256, or equal to it. Okay, if I tell you that it is less than 256, well, ask them if it's less than or bigger than 128. Otherwise, if they tell you that it's bigger than 512 and 256, well, ask them whether it's in between. Okay, so give them 256 plus 128. Okay, which is something like 8, 4, and 3. Okay, 384. Okay, and so on and so forth. And guaranteed that after 10 different steps exactly, you will be able to guess the number. The number ranges between 1 and 1024. Okay, so why 10 steps? Because simply because 1024 is equal to 2 to the power 10. And if you check the process here, so each time you are dividing the set of possible numbers by 2. So after the first guess, if they tell you that the number is less than 512, it means that you have excluded half of the possibilities, and now you are just looking into 12 different values, not in 1024 different values. Again, if they tell you that it's still less than 256 the next time, it means that you have excluded 256 different values, and now you're looking just in one tiny part of it. At the third step, you exclude 128 different values. At the fourth step, you would have excluded 64 different values. And at the end, you will have only two different values. Once you exclude one of them, absolutely, it should be the other one. So maximum in 2 to the power 10, in 10 steps, you can guess one out of the 1024 different values. So I'm sorry, I didn't dedicate a large space to explain this idea. Because I'm not using OneNote, but I think you get the idea, and this is how magically binary search works. Okay, so we know that numbers are sorted from 1 to 1024, and we are asking the person to tell us whether this is greater than, less than, or equal. Okay, well, in searching for a value in a certain array, this works exactly the same way. So the algorithm begins by comparing the element to be found with the middle element. Okay. Um, if the middle element is equal actually to the element that you are looking for, then bingo, big chance you can stop right there. Otherwise, if it's lower, then the search proceeds with the upper half of the list. If it's not lower, then the search proceeds with the lower half of the list. Okay? And we repeat this process until we have a list of size 1. Okay? After that, absolutely, we would have found the element. So if the element we are looking for is equal to the element in the list, then the position is returned. Otherwise, we return 0 or -1 to designate that this element does not exist in the list. Okay? Again, the list should be sorted. Keep this in mind. Okay? But you will see that this, while the first algorithm is sequential, and the sequential one is very naive, so it goes over all the values as if you were playing that game with a friend and you're asking them, is it equal to 1? No. Is it equal to 2? No. Is it equal to 3? So it could be 1024. So it requires, in the worst case, 1024 different iterations to guess. Okay. And particularly if the number is not in the list at the first place, then it would take exactly 1024 different um, uh, attempts to finally find out that the value does not belong to this interval from 1 to 1024. Okay, so even if the guys start giving random numbers between 1 and 1024, it would exhaust the whole list before finding it. Okay, so to avoid this, if you have a sorted list, then go ahead and do it. Later on, we will learn about complexity of algorithm. We will see that, as you noticed here, if we have 2 to the power uh, um, uh, 10, we would have found it in 10 different steps. So it means that the number of steps in required for binary search, if we would have had n, it's, well, think about it. Yeah, it's log of n, okay? Different steps, okay? So no matter what n is, this would have required up to log of n steps to find the value, while linear search requires n different steps. So log is clearly less than n, and this is why binary search is in fact a better algorithm. One last remark, if you think about applications where, such as the phone book, as I said at the beginning, where you are really adding new items. Okay, so few ads are done occasionally. Each time you meet someone new, you add their phone numbers to your list, but this list keeps increasing in size. So if you take the effort to put the value at the right place, I mean to keep your list sorted all the time, then the big benefit is that you can perform search and which you do usually so often that you often do regularly, frequently. You can do it with a much better performance. So just take care of adding the elements in a certain way, so to enable in the future making a binary search. Okay, and this works perfectly for plenty of applications, including when you have, for example, a phone book, for example. Okay, so we spend our time looking for people we know in the phone book to call them, but we add rarely new entries. Good. So how does it work? In terms of code, you have to create two different indices. Okay, I like to call them maybe lower bound and upper bound. Okay, at the beginning, the lower bound is equal to 1 and the upper bound is equal to n, because we don't want to miss any value. We want to consider the middle, the exact middle of the array. So we define middle to be the floor of I plus j over 2. Okay, so no matter what I and j are. And this formula, by the way, works even if you want to look up inside a portion of the array. Okay, so only from A30 to A50, for example. Okay, so just tiny part of it. So we start with whatever beginning index or lower bound, and whatever upper bound you have. I'm sorry, so I wrote bound instead of upper bound. Okay, and then you sum up the lower bound with the upper bound and you divide by 2, and you take the floor of it. Okay, so once this is done, this index is the middle. Okay, we check if x is so I personally like to start with the check whether x is equal to am. Okay, which is done actually here. If x is equal to am, then the location is equal to that m. Okay, otherwise, if it's not equal, it could be greater than am, and in this case, so this is I and this is j at any moment in the life span of this algorithm. So at the beginning, they could be pointing towards 1 and towards n, but later on they would change. Okay, so m is here in the middle. Okay, and we compare with am. Okay, if x happens to be strictly greater than am, so if it's equal to am, we return m right away. If strictly greater than am, it means that it is in this portion of the array. So we actually have to update I, we have to move the lower bound up to m. So we put lower bound equal, it's used to check am itself. So we start with m plus 1. Okay, so we push this boundary I to m plus 1 actually. Okay, and we start looking at this half of the array. Otherwise, we consider uh, pushing j backward, okay, in this case, because if x is not equal to am, then x must be equal to, must belong to this half of the array, okay? And in this case, we put j to be, the new j to be equal to m. In this case, we search in this zone of the array, okay? So once again, we would have excluded half of the values at every iteration. And finally, if x is equal to I, so we keep on doing this as long as I is less than j. And when we go out of this loop, okay, we will find out that finally x would have been equal to AI. Okay, so because we go out of it when I becomes greater than or equal to j, it means they start interleaving in that direction. So I becomes here and j becomes there. Okay, they could become equal at a certain moment, but they may also jump in the other direction. So when this becomes true, we stop the condition, and in this case, we will find out that x would be equal to that AI, okay, to the element in the middle. And in this case, we return the location I. Otherwise, it means if x is still different than AI, it means that we would have scanned the whole array and we couldn't find X in the array. And this is why we return the default um, in, incorrect location, which is 0 or -1. Okay, so let's try it on this example. So here we have 16 different values, and the eighth value is here at 10. Since 19 that we are looking for is uh, strictly greater than 10, then we further restrict our search to the positions from 9 through 16. So now we will be looking at this section of the list of values. Okay, um, good. So now this is I and this is J. Okay, J is still the same, but I becomes equal to m plus 1, which is m was 8, and now we are looking at 9. Half of this value is actually 16. Actually, the 12th position, okay, which has the value 16 here. Okay. So even if we have an odd number, so we consider the floor of I plus j over 2. So now the midpoint is the 12th position with the value of 16. 19 is strictly greater than 16. This is why we reduce our array to those values here, 18 up to 22. Okay. Uh, this is I, this is j. It's 16 plus 15, 14, 13. Okay, so 16 plus 13 over 2. So this gives us a floor, of course, of them. So this gives us the midpoint is equal to 14. And since 19 is not strictly greater than 19, we will stop the search. So here we are stopping not because I exceeds j, but simply because this condition is not true anymore, actually. Okay, so the search is now actually, sorry. So so 19 is not strictly greater than 19. Um, in this case, we get j backward. Okay, so we assign j to the midpoint here, and we still have I there. If we consider half of this array, so it's the 13th position. 19 is strictly greater than 18, then we have to push I further. Okay, and now I is looking at this position and j is looking at that position. Okay, both of them. It's not anymore the case that I is strictly less than j. Okay, so I becomes equal to j. Okay, and which is equal to 14. So we have to stop the loop, and we jump out of it, and we test for the equality with a number I. So I is equal to 19, and j is equal, sorry, to 14, and j is equal to 14. So we check with AI, doesn't matter whether it's AI or AJ, and we find out that that value is equal to 19, and this is why we return the value um, of that location. Okay, so I think the location 14 is returned. Okay, good. Okay, so in the next video, I will be talking about sorting. We will consider two different sorting algorithm, as you will see. So yeah, we will have bubble sort and insertion sort. Just stay tuned for this second video.